Again, welcome everybody for this fun. This is a fun webinar to do because it helps you learn how to do things on Expanse interactively. So in the webinar, we'll talk about what's the difference between regular computing on an HPC system and doing interactive computing. So that's what, and then some tools for accomplishing that in scenarios for when you might be wanting to do interactive computing. So the complex program is comprehensive learning for end users to effectively utilize cyber infrastructure. This is the program's goal is to work with people doing really high-end computing and advanced computational work or domain science work, but you're not writing parallel code, you're using the tools that are on the system. So it helps you get familiar with what you need to know to get started on systems like Expanse, although we try to keep the material general to any HPC system. We do, a lot of our examples are developed on Expanse. So in this talk, I'll define what we mean by interactive high performance computing, looking at how to access interactive nodes, and then some application examples for what you can do. We'll talk briefly about those. So the supercomputers allow you to do really amazing things and do advanced scientific computing in all the domains of science you can think of. And that's great. But they're typically very highly parallel or use very large memory. But not all jobs run sort of in the background. And to run them, you have to run your jobs on these high performance computing clusters. And I'll talk a little more about the architecture, but this is a cartoon architecture of you, the user, logging into something that we call the head node or the login node. You don't initially log right into the computing nodes, which are behind some hardware and firewalls, safety, security, and also allocation. We have hundreds of nodes on Expanse, and it's growing every day. And how would you know which node is the best one for you to run? So I'll talk about how those decisions get made as to whether you're going to use node 1 or node 500, or which core you would be using on those nodes. So there's systems that facilitate your getting onto these resources, and then you can run different kinds of jobs. Command line, lots of things you can run from the command line. You can run jobs using the batch queue system, which would automatically select and run your job for you. You can have different application clients, like PyTorch is becoming very popular today, and other applications. And you can have jobs that use one core to thousands of nodes, depending on the system you're on. And for large jobs, we use schedulers to make sure that the jobs are being coordinated. And I'll talk not too much. We have a whole complex webinar on how batch computing works, and you can go look at that. I'll briefly touch on that. So the architecture for an HPC system, that's a picture of Expanse right there with liquid cooling, and it's right in the main building at SDSC. And it's got these racks, which have multiple nodes on the racks, and we have multiple racks. Each of these nodes would have CPU architecture, AMD EPYC CPUs, and then each node has also GPUs. So the design of Expanse is to give large-scale compute capability to jobs that need a modest number of resources. And so we're sort of in what's like a medium scale for computational resources. If you need a million nodes, then you go to a bigger system. But for Expanse, we have it designed for what we call the long tail of science. Anyway, you've got all this hardware, and schedulers decide which piece of the hardware is available and what your job would best map to. And that's a job best left to the schedulers. We have high performance storage, and we also have large scale high performance networking behind on Expanse, and then external, we connect to advanced networks external, depending on where you're trying to work. We can't change the bandwidth to your house, but we do have high bandwidth between our resources. Okay, so You can run high performance computing jobs in two ways. One is as a batch job, which means running in the background. You write a script, you submit it to the batch queuing system, and then again, it makes a decision as to where your job is best run. It reserves the nodes, it does all this allocation of the job. Or you can run it interactively, like log on, get into the interactive node. We'll talk about how to do that, where you may run a Jupyter notebook. That's the most common scenario, but there's visualization applications that run interactively on a batch job, like MATLAB. We support MATLAB and R, and those are what we would call real time. And the scenario is you might be you've run a job and now you've got hundreds of gigabytes or a petabyte of data. You can't get that on your laptop. So you need to interact with your data and check it all out and maybe do some preliminary filtering. And you can do that on an interactive node where you have access to the data and it's all on internal on Expanse, and it facilitates your post data processing, for example. And again, notebooks are very popular, and we have a secure way to run notebooks, and I'll talk about that today. And what happens when you submit a job, just to kind of give you an overview, is that this is for a system called Torque, which is on a different kind of system. We use Slurm. You have all these nodes where you can submit your job, multiple people submit, and the resource manager makes a decision about what queuing line or what queuing system it would go into, and then launches the job for you, gets the job running on the compute nodes, and really importantly, when the job is done, it gathers up all the data and puts it into an output file for you. So they're very, very, very important, and they're really expensive on HPC systems, but you have to trust that they do their job. So now let's talk a little bit more about batch computing. So high performance computing or high throughput computing systems, again, have a large number of machines that are integrated, and they share the computational resources, and we try to keep that fair. Fairness is based on, for computing, what do you need, and the policies and limits that are set to the queuing system, making decisions. It looks at your job and then starts planning ahead for when, if you needed a whole lot of nodes, it would have to let that node become available, and it tracks things like that. And if we didn't have that, you would be trying to pick out of the 700 nodes on Expanse. You would be trying to pick a node, and you and 20 other people might pick that same node. So the scheduler keeps fairness in mind. And these are what we call batch queuing systems, and there's many flavors of them. Again, we use something called Slurm. They all have these common features: a scheduler for allocating the resources, a couple of queues to which the jobs are submitted. Like we have the main queue, which has a limit of 48 hours and so many nodes or cores that you can run on it. There's queues that are high speed in the sense of you can get things through faster, but you're going to pay more SUs, which are the dollar on the resource on a supercomputer is a service unit, or an hour on the computer. So there's different queues and different policies. We have a debug queue, which is limited to 30 minutes, and jobs move very quickly through it. It's great for testing and developing. And then these where jobs can run are on what we call a partition. So you need a basic understanding, and this presentation goes very lightly over queues, and we do have a complex presentation on that topic that you can go look at. So the main goals are to minimize times between when you submit your job and when you get your answer, and optimize the utilization of our CPUs. So we don't want them all sitting idle. So its job is to maximize how the CPUs are getting used, and maximize basically job throughput, and support these running jobs as they're running in the background. So you can submit your job, go get a cup of coffee, and that afternoon or a day or two later, your job is done. You can get notification on your results, and then finalize the job. At the end, when the job is done, there's a lot of information you can ask the queuing system to collect for you, and some of it does automatically, and you can put that into an output file, and you can specify where it goes. So that's pretty handy to have. So the basic architecture is there's a user, the front node, a job script. You'll write that job script. They're very Unixy, bash-like looking scripts where you define specific variables. And then you submit the job and it goes into the job queue. And then the queuing system, the scheduler makes a decision and gets your job running on the correct number of nodes. So the batch scheduler is the software that implements your script and makes a decision about where it runs. And when you're using the batch system, you don't run the calculations interactively. So your code has to be ready to do all the work in the background. By the way, I see there may be some questions in the chat. We've got a couple people here who can answer them in the chat. And if not, if they build up, they can, the Susan and team can let me know if there's questions that I need to answer. All work is about the same. Some are open source, some cost more money, and some of the batch queuing systems are very expensive. You can imagine if you're on a system like Expanse, where we have hundreds of nodes, that it would be very expensive as opposed to what I might have on my laptop. All right, and this is what we use is the Slurm Resource Manager, simple Linux utility for resource management. And if you're a Futurama fan, it is named after the Slurm drink in Futurama. At our annual meetings, they used to give away cans of Slurm, and it really was bad stuff. Anyway, it's open source and it runs on a lot of systems. It's very popular in the HPC research community, and it's the glue that holds these resources all together. And so it's out again, reminding you its job is to take your script and process it. If there's something wrong with your script, you'll get a rejection on the job with information about what's wrong with your script, and you can correct it and resubmit it. And these are not complicated scripts, although some people can make them very complicated. And we do have a collection of examples with examples about how the batch script should look like. So if you're new, you can start with some of those. But it allocates the nodes. Even the interconnection network is monitored. It has the resources, and the Slurm will launch and manage your job for you. Okay, so how does a scheduler work? If you haven't been on one, this simple example has 6 nodes, and the users submit 9 jobs, and jobs 2 and 9 are what we call multi-node. So this is time going over to the right. And at the beginning, job 1, job 2, job 3, and job 4 get started as the node opens up. And job 1 finishes really quickly. So by then, job 6 is the next one to run, because on node 6, we have job 4, job 5. You can see these are different lengths. Job 2 takes a long time, but when it's done, the nodes open up, so job 9 can run, and job 3 is still running. So it's very complicated how these jobs get scheduled. And this is an example of backfilling so that no CPU stays idle any longer than needed. Batch queuing, batch job submission, most of your work will be done with batch, unless you're running something on something like an interactive notebook. But a lot of your work might be done using the batch queue, and you're very happy with that. So what's interactive computing? I'm interacting with my laptop right now. So for non-HPC, you're all using interactive computing from a computer science perspective. Anytime you hit the keyboard, move your mouse, you're interacting with the computer, and you're actually doing some computing in the back end. The computer's computing, where should I draw this arrow as it moves around, and things like that. So that's really interactive computing. But when you talk about that high performance computing, where there's this big gate between you, the user, and where your jobs run, and that scheduler picking systems for you, designing and adapting that system to interactive computing really only started coming online about 15, 20 years ago, maybe 10. It became more common because we had to think about, what does it mean to not use the batch queuing system to control your job, to terminate your job, to collect all the information from your job. So, but there was a driving need for interactive computing on HPC systems, probably driven by visualizing large data sets. And there are parallel visualizers that run interactively. So it involves the real-time use of the nodes that are available or cores available on an HPC system. And so we have special commands that you can run to grab a node interactively. And when you log on to that node, you're the only person on that node. You own that node for the amount of time you asked for. Usually there's a queuing policy of about 2 hours, I think, on Expanse. So you have to get your work done in that time. And you can do all kinds of tasks. You can develop your code. Some codes take so long and have so many, have a big computational load that they're best done on an interactive node. The login node's very busy, and you can do some compiling and debugging. Compiling, we don't want you running your code on the login nodes. But if you're compiling and debugging, grab an interactive node and get your compiling done there. It will go faster because these are faster and have a larger memory and other resources that the login node doesn't have. So you have it when you use it when you have large data, when your user inputs come via command line interface or a GUI like a notebook or MATLAB or RStudio, and we support all of those. And the actions are the result of user input or program output. All right, so why would you use it? You need more memory. Your job's no longer fit onto the CPU system you have been using, and you're doing things interactively. And that's why we have all these nodes and cores for you to get access to. Expanse has over 768 nodes with 128 cores per node. My MacBook Pro has 1 node and 8 cores. I can still do some modest parallel computing on it, but once I use up the 16 gigs and I'm swapping memory in and out, it's time to go to a bigger system, which is why you guys are all coming to Expanse anyway. You need to move to this bigger system. And so you have too much data, obviously. It has a terabyte of NVMe per node. And so you could do a lot of data processing using a parallel visualizer, for example, like ParaView. And your network is too slow. Expanse connections are in the hundreds of gigabytes per second and growing. And we always have the latest and greatest networks on our systems. And I get right now 300 megabits per second. I could get a gigabit if I want to pay for it, but that's about all I need right now. And if you're in a lab running on your own system, you might have, be doing something with FastQ where the data sets are half a gig. And so to upload one run, you need 360 seconds. So that's kind of the motivation. If you're in that range where you're waiting minutes for your data to download from Amazon Bucket and then minutes and minutes to upload and look at your data, it's time to move to a bigger system like Expanse. Okay, so anyway, real-time user interactions is similar architecture. You have a user on a desktop and you want to connect to a node. First, you have to get that node assigned to you, then get a connection, and the Slurm scheduler still gets that node for you as you're trying to go interactive. And the head nodes are the login nodes, and we have 2 on Expanse. So these real-time user inputs, then once you get directly connected to the node, you can be running an application, but you can also SSH onto your node. And I'll show you an example later. And the examples again are Jupyter Notebooks, ParaView, visualization tools. So, you're going to interact with the data after the job is done. On Unix, these are some of the methods and applications. On Unix, you would look for information on the file. If you have an output with tens of thousands of files, getting over onto an interactive node where you're directly connected to the Lustre file system, you can view your files more quickly. You can figure out where they are. You can look at the output. You can grep and awk large numbers of files. Everything's faster on these interactive nodes. You can look at the file contents from a batch job or the raw data using an explorer like NetCDF. And I'll show you an example of that. The NetCDF data browser is great for right there on the node, looking at your data and visualizing it. And there's many kinds of ways to do that. You can plot your results on the system, and you can use some simple command line graphing utility. I'll talk about GNU plot, but there's other newer versions available. And then for data visualization apps, like last week we had a webinar on the Tau Visualizer and ParaView. These are really the right tools because they're optimized for HPC and they've been around for a long time. And then data analysis platforms, MATLAB and R. Again, to remind you, interactive computing are these interactive environments where you're running a notebook or you're working with ParaView or doing Jupyter Lab or other kinds of MATLAB, other kinds of applications. So we have the open on demand version of a portal, the Expanse user portal. And I'll say this a couple times. We strongly encourage you to use it to run your interactive computing applications, like to launch MATLAB and launch R. The portal shields you from a lot of environmental requirements that you'd have to set up in, like building a Conda environment. You can launch a notebook through the portal, and you can launch Jupyter Lab through the portal. It's just constructed and optimized for some of these high-end interactive applications. So I do want to mention a key point that a lot of interactive services have this key vulnerability. They provide access to your HPC file systems, and it's often over HTTP. So be very careful when you're firing up or even installing your own software on your laptop or on another machine or on Expanse, that you're using HTTPS. We require that. We don't allow any jobs to be run on the login node, first of all. But if you're going to run a Jupyter Notebook, for example, I'll talk about a tool we've got called Galileo to launch a secure HTTPS. But even if you have an HTTPS connection, that HTTPS link right here is still an entry point to all your data, your local files. We have sandboxes around what you can do, but other people could get that. It's like a key, and as long as it's alive, like the 2-hour interactive time limit, that's a key somebody can use to hack into your account. And people try to hack into big systems like Expanse all the time. So be very, very guarded about these links that you get when you're running jobs and you have to step away from your computer. If you're in a public space, for example, make sure you've locked down your system. All right, so let's look at how to access an interactive HPC node. And how am I doing on time? I'm good on time. So you need some application that you want to run, and you want to stage large amounts of data, and you want to have some kind of application like PyTorch or TensorFlow, or you need to compile some large job. So here, these examples here I tested them last night, they worked. You can also find these in the Expanse user guide. Most of the material I put in here are also reflected in our Expanse user guide, and I have a link to that. You can find that online, and a link at the end of my talk. So you should be able to just cut and paste this into the Unix command line to get a CPU or a GPU, and you can ask for more than one or not. So I'll show you examples on how these work. You need to have your own account number. This is mine. It won't work for you. So here's an example of an interactive CPU. There's the srun command asking for, this one is the debug GPU, sorry, and the account, the number of tasks per node, the number of nodes, the memory, the number of GPUs I want, the time, and what shell I want to work in. And so you want to make sure, if you don't know what modules are, go back to some of our introductory material to learn that modules are how we allow you to customize your software environment. Very, very handy to have the ability to reflect the software you're using on one day, which might be different from the next day. And so these are for getting the right compiler and a link to MPI, and then to run a simple code called MPI prime. And it ran, and it goes through N and counts out to all the prime numbers under 500,000. And I cut that. SNP means it was a lot more to fit it on the slide. So we ran the code. Notice I'm on the interactive node and I'm running an MPI or parallel code. this is one of the reasons interactive nodes are great, especially if you're developing parallel code and you can do a small test case on that interactive node. And this time I went to the debug queue and it's only 30 minutes. When you're done, make sure you exit your interactive session because you'll get charged for it if it's still running. And don't oversubscribe your job. Some resource managers allow you to do that, which means if you ask for 16 initially and you ask then for 32, you'll get threads spawned and your program performance might degrade. Some compilers allow it and others don't. It's going to be compiler and system dependent. So some gotchas there. And then this is a duplicate, an example of showing that you're on an NVIDIA node. You use the NVIDIA SMI. And so for you, when you get on a node, you can tell you're on a node because the node ID changes. I wanted to be sure to point that out. Okay. So there are ways to run visualization apps using something called X11 forwarding. I keep this in my talk because some resources out there in the HPC universe allow it and support it, but we're finding that I'm on a Mac and I use Xquartz as part of my X11 software, and it doesn't quite work right. I have figured out ways to make it work, but I wanted to include this to inform you that there are ways to you have to have this to run things interactively and get visualization, for example, to share the graphic images and that graphic data. So the X window system is it's for bitmap displays. Like right now I'm seeing images because the local X windows is working correctly. And it's supposed to be architecture independent, and it pretty much is, but controlling it on an HPC system is a little harder. So you have my workstation, a keyboard, a mouse, a screen. You're seeing my stuff right now. You see my mouse moving around. It talks to the X server, and then it goes output to some X client, which could be local or remote. And if it's remote, it goes over the network. And you can see when I'm launching terminal and I'm typing into that keyboard, I'm actually using some parts of the X11 system. You didn't know that. I remember when it didn't exist, it was really hard to connect to remote systems. So you want to install Mac OS Quartz, and I don't have the PC showing up right now, but I think it's in here. And then there's a command you have to use the -Y, and then you log into Expanse. And I installed Xquartz using Brew on my laptop. So you have to use multiple windows when you're getting connected. And I'll show you a more detailed example. In this simple example, in window 1, I connected to Expanse, and in window 2, I connected to Expanse. Then I got my interactive partition node assigned to me, EXP 955. Now, I'm logged in as the same user, M. Thomas, and so to get directly on that node to run things visually, like MATLAB, I SSH onto that interactive node. And so it's a little bit of work to do it, but it can be done. So GNU plot is an old plotting routine that's really, it's great for when you just want a quick look at data and visualize it from the command line. And you can get very fancy applications, but I figured out that back in this one here, this window needs to be the Xquartz window. It can't be a regular Mac terminal because Xquartz knows about visual, the X11. And so I was able to get GNU plot installed, get the right modules, set the right terminal, and then to plot, but it only comes out right now in black and white. I haven't solved why it's only black and white, but this, we think, we've been looking at it, we think it's due to the X11 Xquartz implementation. But there are other applications that can do this for you as well. So now we're at the interactive visualization examples. So I talked about data files and NetCDF, and data visualization. There's data storage formats. NetCDF is one, HDF is another one, where they're what we call a binary file. They're a really complicated collection of the information associated with your data run, and they're used in big models like weather climate models. And inside the data, inside the file is data variables that you want to save, like the date, the time, the names of your variables, the links to remote sites, any data you want to save associated with that data run and the data. And you can have multiple data in there. You could have arrays, 1D, 2D, 3D, serialized into there. You can have all kinds of data, whatever you need. And so it gets stored, but it's stored in a compressed binary format. So you need a special application, like for NetCDF, NC View and NC Dump are ways we view it. NC Dump shows just a printout. So you can get compressed data storage. And when you're working on big systems, like I said, climate weather model, energy models, they'll be using something like NetCDF to compress the data. And so then you do need this software. So you can then use NC View as a visualization tool for looking at your data. So it's very handy to have that running and that capability to look at your data. Let's say you have a job that's running for multiple days. You can run NC View really quickly on some of the data files and see where your job is and figure out, do you want to keep it running or not? Or it looks good, or, it's a way of also monitoring your jobs as they run. So configure NetCDF, you have to, it's maintained by SciNet Canada, and you have to define some environment variables. You have to compile it, and it is maintained by SDSC, but it's not used very much. So I found it was easier to install it for myself. If you find you need to use NetCDF and you're having trouble, reach out to consult@sdsc.edu and work with the user support team, Nicole, Marty, they're here, and see if they can help you get it running. I don't know that how often it's used, but it can be important depending on your project. So here's an example of setting up the library and include paths. If you haven't ever done that, you put these in your bash profile file, and then set up all the environment variables that they require. And then you want to update the path to the binary for the NetCDF. Like this one, I am actually using something installed by the user support people. And I'll take a short moment to explain to you how valuable and scary this very long path is here. CM/CM shared app spec CPU op spec Linux operating system version and the app. The people who work in user support and the operations group work very, very hard to do clean, updated versions of all the software that are commonly used. And every once in a while, somebody comes around with new, and they're happy to work with you to see if we can get it running. But the implementations are OS dependent, they're version dependent. We have multiple dependencies, and you find them all in CM shared apps. And there's also examples of code that work, and you can find singularity containers. I'll talk about that in a moment. But everything, if you start fiddling and looking in CM shared apps, you don't have permission to write. So you can go and browse in there and take a look at everything. It's rich with information about what kind of software you can use when you're on a system like Expanse. So it's a lot of work to maintain, but feel free to try and take advantage of software in there that's in your use case scenario. Okay, so I found where I know where my binaries are. And so now I start building the module environment that I need to load and run NetCDF locally. And I can verify that my install worked, because if I do which ncdump, and which is a Unix command that allows you to find the location of an application that the system knows about, and it found it. If this didn't work, the module environment, then this which ncdump would say not found and give you back an error message. And so I look for ncdump for core dumping my data, and ncview for viewing my data. And those are both found, which means I should be able to use them. So I have an example. I'll give you a link to HPC training-examples. You can find a lot of example code in that /CM shared directories. There's multiple examples, and I also have a collection associated with our training material. And I'll give you the link for this in a GitHub repository. And so I ran it. It's a simple C code, easy to compile. And I ran it and I got some output data files. And so here's an NC dump with help for all the things you can do. And then here's the net NC data files. And I print out the data simple, which shows you the complex information you can get, even the dimensions of these two main arrays called X and Y. And then I can have it show me the actual data. And I think that's on the next one. So I took a few minutes to go through this, and now we can also run NC View and visualize the data. And this takes a little bit of learning, but there's other applications that work similarly. This is just an example of what you need to go through to install something like that you might want to use. But I'm going to start pressing the idea that if you can run it through our portal, and most of these are available through the portal, then do. The portal's got it all maintained. And if there's something not working, you report it and they fix it. So I show you the joy and pleasure of running something like NetCDF. Oh, I got it running. I can view my data, but also the pain required to install it. So if you can use something we've already installed or work with us, or if it's in the portal, even better, your experience will be smoother and more productive. All right, so we've looked at basic things that you can do from the command line. It's rich, and you may be already doing something that I don't even know about. I'd be interested in hearing what you're able to get done. And then we have platforms that we're installing and supporting, and the gateways and portals. So here is running MATLAB from the command line. Really recommend against it. It ran for me last night, but when there's lots of people on using all the resources, it can be, or if you have a bad connection, it can be really slow. So you can get an interactive node, you load the right environment, check that you've got it, launch MATLAB, and up comes MATLAB. But nothing happened in this example. I wrote a command to plot it, and nothing happened because I was in a non-X11 aware window. So in this slide, I show you how to do the same thing. You have two windows. Window 1, you connect, you SSH to window 1 and window 2. Window 1, we get the interactive node, but window 2 is an X11 aware. So I used the Mac app to launch an X11 aware window, exports. And so that's window 2. And I use that to directly log on to the interactive node, and then my MATLAB works. So boom, it works, but it's very, very, very slow. We support this on the portal. Use the portal to run MATLAB. Don't even try the command line. You have the same capabilities. It launches MATLAB, and it's going to run better and be easier for you to run, and it will have a guarantee. When I hand load everything, I may or may not have the most updated environment, but the portal always has the upload. It always has the right environment. So we always do a lot of our training on the portal, and things like MATLAB and R and notebooks will run much more smoothly. Also from the portal, well, we can show you, you can get a terminal. So it does quite a bit. You can run R from the command line, but only on the TSCC, the Triton Shared Compute Cluster. If you want to run R on Expanse, use the portal. So, but this is just an example of how you would do it on the Triton Shared Computing Cluster, which is a hotel cluster for UCSD researchers that they all buy into and partially own and use and share. It's a great system too if you're part of UCSD. Okay, again, for the GUI, use the Expanse portal. The next thing is Jupyter Notebooks. These days, most people know what it is, but in case you don't, It's an open source interactive web tool that allows you to write Python code or a couple of other languages, depending on, you can get a kernel for C and even Fortran, but Python is the most popular one inside the notebook. And you can run code that does analysis, visualization. They're pretty powerful. And this is an example. You can do notebooks. You can do one notebook. You can do Jupyter Lab and run multiple notebooks, or Jupyter Hub is a service that might be hosted somewhere. We don't host Jupyter Hub because the security model is not strong enough for what we want to do on Expanse, but we do support running Jupyter Lab and Jupyter Notebooks using Galileo. So we'll get into that quickly. All right, so to run secure notebooks, again, by default, Jupyter launches a notebook in a web browser with an HTTP connection, which is not secure. And so we want to make sure you have security all the time. So locally on your laptop, it's not such an issue. Most of us use Anaconda, and it doesn't have to worry about the external world because everything's running on your laptop. But it's still a vulnerability that if somebody came by your laptop and the browser was open, they could access your system or share that URL if you're opening ports. You have to be really careful. So to run remotely, like on Expanse or another machine, you can either connect over HTTP, which is the default, but it's insecure. You can use HTTP with SSH tunneling, so you make two connections. One is the HTTP, and then the SSH tunneling is where the data moves. And those are great, but it's not convenient and it's not robust. Connections, SSH tunneling connections break. You can connect over HTTP using the satellite reverse proxy service and the Galileo client, which we developed here at SDSC. Galileo's great. You just one command and up comes your secure Jupyter notebooks on the machine you want to be working on, even in a directory that you want to specify. And so we'll go over this really quickly. Next. Okay, so the reverse proxy service is part of the internal network, and it's what connects you, the external user, to an interactive node and produces an HTTPS URL for you to connect back to that interactive node securely. And so Galileo is an application that is the application. You will pass several arguments to it to get your notebook fired up. And Marty Candace has done an amazing job of maintaining and advancing Galileo. And you can start any kind of Jupyter jobs that you want. And he's working on generalizing it, but for right now, it's mainly for launching notebooks. And we're getting a little late in the time period, so I want to get into showing you a couple of examples. So you're on your laptop, and you need to run a notebook on Expanse because it has large memory requirements. You need an interactive job. So you can SSH onto Expanse, and then you can you can run Galileo and then get this internally. There's a connection, which is not HTTP, but we don't worry about that because we have a firewall. But what you get back is a wonky looking, randomly generated connection made by the satellite reverse proxy service. You'll put this into your web browser and wait for the interactive node to be allocated and all this other stuff getting set up. That's what Galileo does for you in the background. And then all of a sudden up will come your notebook and you can run your job on that. It's very popular. So here's an example of the Galileo input arguments that you can use. Some are minimal, and it has a very good error messaging system. If you don't get something right, you get responses back. And then it takes a while. Once you submit it, it takes a while to get the node assigned to you. So we have a status bar that you'll get. You put your URL, your secure URL, into the window, the browser window. And when all of these states are accomplished, you'll have 4 green balls, and boom, up will come your Jupyter Notebook or Jupyter Lab, where you can see you're in some notebook examples. Hello World, this is my directory on Expanse. And then you can start running your Jupyter Notebook. You can add new notebooks. You can have whatever features that you get out of Jupyter Lab or Jupyter Notebook, you'll see when you launch it on Expanse. Okay, so more detail in, because it's hard to read a little picture. These are the kinds of examples. And if you go to Marty's Galileo page, he does an excellent job of maintaining it, keeping it updated, and you can literally cut and paste a generic command and get it running. And he's in user support, so he's really sensitive to the needs of people. If you have problems, send a note to support to consult@sdsc.edu, and we'll help you resolve whatever you have, whatever problems you have. So that's from the command line. And again, it interacts with satellite and then the Slurm manager and configures the software environment for you, generates that batch job script, saves a copy for you. And it's in quiet mode in the portal. You can run you can launch notebooks from the portal, and it will do Galileo in the back end. These are just some details showing you how you have to set up a path environment. You have to make sure that Galileo is in your path, and and it will be if you put that into your batch profile file. You launch Galileo, and you'll get some output, a whole lot, but then it will say submitted a job. And when ready, you get your Jupyter Notebook session connection, which is this URL. Put that in your web browser and then start waiting for the 3 balls to light up. So here we're still getting set up, and it can take a long time if there's a lot of jobs running. So you can log on to Expanse and you can look at your job IDs, because you get the job ID here, right there. Whoops, you get the job ID right there. So you can log on, you can take a look and see how many jobs and what's the status of the job. But remember to treat your notebook URL as a password. Okay, and it's the same for a CPU or a GPU. And you want to verify, if you want to make sure you're on a GPU, you can put in a little command in your notebook to run the NVIDIA SMI command. If you're not on a GPU, that will fail. Go back and revisit your Galileo command and what you requested. All right, so notebook examples. We have a collection of notebooks. This link is in the back of the talk, but it's github.com sdsc-hpc-training.org Expanse notebooks. We test them every spring or summer, and there's different kinds. Some are for CPU, some are for GPU, but you should be able to download this collection and then launch a Jupyter Notebook and go find that folder on Expanse. You can clone this collection and then test out and make sure, do that, because then you can make sure your whole environment's working. Okay, so gateways, we've gone through a few of these, and you guys may know MATLAB or R, but through the portal, you can run all of these: notebooks, MATLAB, and R. And you can also run through the portal a shell. You can connect to a terminal. So this is just a cartoon picture of when you get logged in. Your landing page will have options for features. You can look at files. You can look at run interactive jobs through the portal, MATLAB, notebooks. You can build jobs to submit to the Expanse queuing system. You can look at your files and look at your output data. And you can look and see how many jobs are running and whether they're finished or not. So it's very secure, and you can log into it with your access ID. And if you can't, then submit a note to make sure, you know, we figure out why you're unable to. So again, these are just zeroing in. You can open a terminal, and this is an SSH. It's as if you SSH on. What's great about this, though, is you can have multiple terminals. You just have multiple tabs in your browser, or pull them out into separate windows. You have a full shell access, and you can do anything there that you would as if you had SSH'd on from your terminal app on Mac OS or something else on Windows. But what's nice is you're in that portal environment. So a lot of environment variables that you need to have set up, they come already set up. So, you know, try that out and see if you can like it. And there's an example of running MATLAB. It can take a few minutes to run MATLAB or launch the notebook because you have to get that interactive node. And there's a form input screen where you need to be able to tell it a few pieces of information so the system knows what kind of MATLAB environment you need. And the same for launching a notebook. You launch a Jupyter session, and I have an example of a Jupyter session input for all of these form elements that should work. When it works, you get a message. When it doesn't, you get this ugly pink colored thing and there's a problem. If you've been running a notebook and you come back in and you try to run it and it doesn't work and you haven't made any changes, get in touch with Consult because it's probably not you. Might be something else going wrong. Anyway, here's the launch notebook. And so on this next screen here, my account is use 300. You need your own account. That won't work for you. What partition you want, and then how long you want it to run, how many cores you want, how much memory you have to specify that, how many GPUs you want to use if you want to use them. And we use containers. We recommend using containers on Expanse because it gives you a really well-defined self-contained environment. So this one here should work for you. It's PyTorch. There are many in CM Shared Apps containers, Singularity. There's a whole slew of them, TensorFlow, PyTorch, some of them customized to particular examples. And if you're trying to build one or you need one, reach out to user support and see, if there's one that already does what you need, but it's named something else that it's not named what you might expect it to be. Talk to them to find out which container might work better for you. If you can use one already built by our user support people, you'll be better off. And they can also consider making a change to it, add in any feature you might need. What environment you want, Singularity Pro. Remember, specify your container and specify that Singularity Pro environment. We use Singularity as opposed to Docker's because Singularity is more secure and does more what we need on Expanse. Conda environment, if you want to add any of your own, and you may have to do some testing, a YAML file, you can add that in. And if you're having an interest in that, there is a talk by Peter Rose on our training on demand site that you can go see his recommendation for some of these. And if you need Mamba, new caching mechanisms, I rarely use those. And don't need a reservation. If you were in a training class, we would specify a reservation. And your working directory is recommended to be home, but it could be a particular subfolder on your Expanse system, and you can specify that and launch Jupyter Lab, for example. These should work for you. Cut and paste, these should work. If not, let me know so I can correct my slide. Okay, and that's it for my presentation on interactive computing. And do you have any questions? Thank you for your attention.